Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
In the four-part series on vision-based modeling, and today I'm going to be talking about how to build three-dimensional models from images. Last week we discussed how to figure out where the cameras were and where the points were in 3D, and today we're actually going to talk about how to match up pixels and build complete surface models. So the first few slides are the same ones you saw last week, so I'll really zip through them, but for the benefits of anyone who wasn't here last week, we're looking at computer vision problems, which are the inverse of computer graphics, so how to go from images to three-dimensional models. And kinds of applications we can do with this are, for example, building virtual reality model or CAD models, things you might do in computer animation. We're striving for things that are photorealistic. We also want to get away from necessarily having people construct all the computer graphics models by hand. And more things are becoming feasible as these technologies mature. So sample applications are things like trying to figure out where a camera is relative to a live scene so that you can superimpose graphics, or building three-dimensional models from a series of images. For example, the facade system that was presented, SIGGRAPH in 96 is an example of that. And we'd like to build these kinds of 3D models as automatically as possible. So this is just an example of the kind of results you can get. Starting from a sequence of images, you can build a volumetric model like this octree, or you could, for example, match curves and get a curved model like that lying on the surface. Starting from either one, you can build a triangulated model and then project the color images back onto it, and that's the kind of model you get. So while this is a single static image, there's actually a three-dimensional model lying under this. So here's the outline for what we're going to do. Last week, we covered camera calibration and pose estimation, figuring out where points are in 3D, and then solving the whole problem all at once, which is when you have a bunch of images and you don't know anything about the cameras or the geometry. And today I'm going to concentrate more on the matching. In other words, how do you, given two or more images, how do you figure out which parts go with which, and then from there, how do you get a dense shape model? So I'm going to start with feature matching, which is just looking at things locally in a very unconstrained way. That's a very quick review. And then I'll go through a series of stereo matching algorithms. This sort of gives you an idea of the range of things that people are working on, but several of these are things I've developed over the last few years. And then I'll review some older work I've done on building volumetric models and surface models, and talk a little bit about inverse texture mapping. So let's get started on feature matching. So this, in a sense, has already been covered by Anandan, but let me just go over this again. If you have a certain region in one image here, like this red square, and you want to find where it is in the other image, like let's say the corresponding location in the other image is this green square, but the eye is shifted, so you really want to be where the red one is. How do you find that? There are all these techniques called correlation techniques, which basically compare pixels in a variety of moving square windows and find the ones where the match is the best. And this is the simplest possible match you could do, which is just the sum of squared differences, or a linear regression between the two. So you compute the sum of squared differences between corresponding pixels, and then that gives you a cost for a particular pixel xy with a displacement uv. So you can do this for a number of different displacements and then find the one that has the minimum error. And if you want to get some sort of a subpixel precision, there are several ways you can do that. One of them is to actually use a Taylor series expansion. So what we do here is the error term is the original difference between the two images. And then if we do a Taylor series expansion in terms of the image gradient, G, and the infinitesimal motion, U, we end up with this kind of an equation. This is, again, a sum of squares in the quantity U, but now we actually have a full linear regression, so we can find a real valued solution for the element delta U, and this is called the Lucas-Canati algorithm. This was developed in 81. So we end up solving this 2x2 system. Now, in practice, people don't actually do this on a per pixel basis because you can only get sub-pixel motions. You want to be able to solve for larger motions, and so you use a pyramid where you start at a smaller image that's been subsampled, find the best motion at each pixel that you care about, and then do that at the next level of the pyramid using that as a starting guess. And it turns out that these equations here are related to the brightness constancy equation, which was one of the fundamental motion things that I had uncovered. So I'm just sort of bringing this up again to bring you up to speed that, yes, if you wanted to, you could exhaustively search, pick up each pixel in one image, go find where it is in the other image, and that's one way of doing correspondence. And sometimes, if you're trying to, for example, figure out where the cameras are, that's a very sensible strategy. You'll find pixels where it's easy to do this, where the left-hand side has very good singular values, and that means it's a well-localizable point. You'll find hundreds of these points, find them in the other image, and get started like that. But that's really not what I want to talk about today. I want to talk about what happens once you know where the cameras are, because the problem gets a lot easier. Basically, if you know where the cameras are, then for any one pixel, let's say we're trying to match this pixel here at the corner of the diamond in the center image, and we want to say, okay, let's find where it is in the other images. If you know where the cameras are in 3D, you have mathematical models for that, then that pixel can only be somewhere along this green line, because that pixel, when connected to the camera center, projects this yellow ray. The image of that yellow ray in the other image is this green line, and that's called the epipolar line. So that means you've reduced the search for correspondence from a general two-dimensional problem to a one-dimensional problem. It's not only faster, but just in general much more reliable. So for example, if we have a pixel at the left edge of this cup, and pick any one pixel here, that projects to a line which allows us to intersect that line with this left edge. So even things which might be ambiguous matches, like continuous contours, once we have the epipolar geometry, become unambiguous in the general case. So there's a trick you can do when you have only two images that makes the problem even simpler, which is you can rectify the images. So what happens is, if you look at the previous image, this line here is the projection of this ray. It turns out if I project this line all the way back to this camera, it forms another line. Basically, this line forms a plane containing these two camera centers and the line in one image. Therefore, it projects to another image as a line. Now, in the general case, this will not project to a line in the third image. This green line here is just the projection of that yellow ray. But if I were to ask, what is the projection of this green line into that image, in general, you're projecting a plane into some other camera, and it won't necessarily project as a single line. The exception is when all the cameras are collinear, in which case you can rectify all of them simultaneously. But there's many different ways to do the rectification. If you're working with two images or a set of collinear images, this makes life very easy because, for example, if you rectify the images such that horizontal lines correspond, you only have to do one-dimensional search along each line. So it's a very commonly used trick, although it doesn't apply when you have many images that you're trying to match simultaneously. So, given that trick, this is a very standard formulation of the stereo matching problem. So if we have an image sequence that looks like this, here is just a sequence of images of a little forest scene that were taken moving the camera sideways. You can get a depth map that looks like this. So the way to interpret these depth maps is the pixels that are lighter are closer to the viewer, and the pixels that are darker are further away. And you can see that the algorithm makes a fair number of mistakes. It gets these little dark blotches right here. But roughly speaking, it's recovered the fact that there is the tree in the foreground, there's a sloping grass here, and in the background there are some leaves here in the midground, and then some things very far away in the background. So it's mostly gotten it right. And this level of quality is kind of what we expect today in the real-time stereo system. So for example, Steve Schaefer's Easy Living Group has a real-time stereo matcher. If you look at the quality of their outputs, it'll be comparable to this. It might be a little bit less noisy, but it'll make mistakes from time to time. If you're trying to locate where a person is in a room, for example, it's a perfectly good sensor. It'll give you the information that you need. So I was just going to mention that that trick I said about searching for features using a pyramid can also be applied to stereo. The way it would work is you would first generate a smaller version of this image. You'd run stereo matching, and then at the next finer resolution, larger image, you would restrict your search range. So you don't search far away in terms of pixels. By restricting your search range, you not only have a faster algorithm, but again, you have less chance to make errors. So that's hierarchical matching. Another thing to keep in mind, if you're going to use this for further applications, like let's say you're going to take these depth measurements and then try to integrate them over time or fit a surface to them, is that not only do you have a depth map, and here you can see that this is another representation where we pseudo-colored it. So here blue is closer to the viewer, green is midground, red is further back. But here you'll notice that in the areas where there is no texture, like back here, we have pretty much noise because the algorithm is free to make up any depth that it wants to. They're all reasonable matching depths. So a good thing to compute is the certainty map. And so some of the stereo matching algorithms, as you ask them, will actually tell you, yes, here we have very good edges, and therefore we have a high certainty, and here we have almost no certainty. So you can think of this, for example, you could take the depth map, threshold things that have keep only things that have a very high certainty, and then do some kind of a surface fit to get your final model. So that's an important thing to keep in mind. Okay, and here's an example of how these things can be used. The input here is a collection of images taken in my old office back at Digital. And the kind of depth map we computed was this thing. You can see it's reasonably smooth. It was computed using a spline-like representation for the depth. And this is a novel view. So here we have a sideways view of that same scene. So you can actually basically take new views of things. Now, this kind of an approach, which is take a depth map and take a collection of images, compute a depth map, is, as I said, useful for things like locating people. It's also useful for limited amounts of sort of 3D simulation. Like if you want to, for example, put something up in 3D glasses or turn an object a little bit, you'll get a reasonable sense of depth. But there are problems with this kind of approach. As I said before, it fails in textureless areas, and so it won't give you information there. Also, in general, stereo matching is sensitive to things like specularities and things like that. But the biggest problem is that near the edges, these algorithms typically have problems. And there are two reasons for that. One is, think of an algorithm that is moving a window around, and the window happens to straddle this foreground-background thing here. So if the background is textured enough, a square window sitting totally on the background will correctly match the background. One sitting totally on the foreground will correctly match the foreground. And a window that straddles the foreground and the background will have conflicting results. Some of the pixels will match well at one depth, other ones will match well at another depth. And if you kind of just sum them all up in a least square sense, then the foreground or the background will win in a way that isn't very pleasant. It might, for example, the thing that has a higher contrast might win out. So typically these algorithms have this big fat area around the foreground where they misclassify. Again, if you're using this for like recognition or avoidance, it's not a problem. But if I was to take this object with a big fat foreground and let's say try to insert a synthetic element, so let's say this is Jurassic Park and we want to make a dinosaur, put a dinosaur behind one of the trees, we would see the wrong color pixels clinging to the tree. So that's just not acceptable. And I'm going to, pretty soon tell you about other variants that try to overcome this problem. Now, another thing is, let's say I gave you an algorithm that was very, very clever and actually managed to label the correct depth of each pixel in this scene, as the foreground or the background. The question is, are you done? Well, what does it mean to correctly label this pixel here? This pixel is some mixture of the gray foreground sweater color and the yellow background log color. And yes, I could say, well, the depth of that pixel is the foreground. I could make an arbitrary decision. But think again of inserting another element, a dinosaur, behind this person. What would you really like to happen? Well, computer graphics people figured out that unless the foreground object has what they call an alpha matte, unless there is a partial amount of foreground color that'll get blended in a soft way with the new element that's behind it, you won't have reasonable synthesis. So we should be asking our stereo algorithms to deliver not only the correct depth at each pixel, but also the correct opacity and the correct color. So it would take these pixels, which are mixtures of brown and yellow, and for those pixels that it assigns to the foreground layer, it would make them a pure brown with a partial transparency. Okay? So that's what I'm suggesting should be the goal of newer generation stereo algorithms.
You get two disparities also?
Yes, you would get two disparities, right? And the representation, I'm going to go through a series of representations of how you could do that, right? For those people who've been following the new work in image-based rendering, something like a layered depth image is one candidate, but I'll show you several possible candidates for that. Yep. So I think I've already gone over that. What we'd like to do is recover the depths, colors, and opacities We'd like to do something well at occlusions. We'd also like to be able to use as many cameras as possible, so we're not just limited to 2 cameras. And the details of this algorithm, I'm going to present some details here, but the full details are in an ICCB paper that I presented. This was done with Polina Gollin, who was a summer student here. So let's look a little bit at the geometry of the problem. Think about taking one of these cameras called the virtual camera. For those of you who are familiar with layer depth images, this is sort of the coordinate frame of the layer depth image representation. And think of sweeping a collection of planes, let's say a set of parallel planes, backwards through space. Each of these planes maps into another image by a 2-dimensional perspective transform that people call homographies. So you can represent that with a 3x3 matrix. It's sort of like a quadratic interpolation of the 4 corner points, but it's actually a rational perspective interpolation. So for any one plane location, those pixels on the plane would map to a particular set of coordinates or pixels in any one input image. Okay? So this is sort of a multi-frame thing. And furthermore, if you have several images, then each image will have its own corresponding set of pixels. So this foreground green square would project to a different trapezoid in each image, and those trapezoids would say which pixels go with which. So another way of saying it is, for a particular pixel in the virtual camera, let's say the upper left corner, at a particular depth, I can figure out where it lies in the input image. And I can do that for every single input image. So if I do that, if I say, for a particular depth value d, for a particular location x, y, and for a particular input image k, what is the pixel color? I can read all of those out directly from the input image. Furthermore, I can stack them up in a little, if I take this thing here going across k, which is the number of input images, into a little stack, I have a bunch of color samples which, if we're matching correctly, should all be the same color, modulo noise. So I can actually compute its mean and variance in that color sample. Okay? And this is sort of the essence of what I would call a multi-image matching or a space sweep approach. That rather than saying, well, I have one image, and where is it in the other image, and where is it in the other image, you think of it more as, I have a volume of space, and I want to know whether a particular location in space is a good one. And so I will look in all the images and see if things agree. Okay. So here's what plane sweep looks like when you have multiple images. You start with your virtual camera, and then you start sweeping the planes back, and you say, okay, for that plane, if the camera was actually, if the object were to live on that plane, what happens when I warp all of the images together and blend them? And then I go and try another plane. So there's one plane, there's another one, there's another one. Each plane defines a slightly different region in the input image. You blend them all together, and during the blending you also compute how much they're in agreement, and you base your decisions based on that. So, and that's just pointing out that this sweep of space is some kind of a projective resampling of your 3-dimensional space. So here's what it looks like if I showed you just what the blend images look like. So this is a flower garden sequence where there's a tree moving in the foreground, a big fat tree here, and there's a house in the background and a smaller tree here. Focus, for example, on this thin tree back here and look at how, as I sweep, it comes into focus and then goes out of focus again. So it goes out of focus, in, and out of focus. So this isn't actually the way the stereo algorithm works. It doesn't compute the focus, although, Francois was asking me today, why not? There's no really good reason. I think it might be worth exploring this. But my intuition has always been that just by looking at the errors between pixels rather than looking at something spatial like the amount of focus is more useful. But in essence, I could have also been plotting the error images, and I think Chris Bueller extended this piece of software to actually plot those out. And basically, when things are in focus, the error also goes down, and that's what you're looking for. You're looking for depths at which the error goes down. Now, just computing the depths at a single pixel is a little bit erroneous, both because there's imaging noise and because in something like a textured pattern, there might be accidental alignments or something like that. So typically what you want to do is what I call here aggregate spatially. In other words, you can compute this error, but it's also good to do some kind of a summation over your neighbors in order to see if there's a consensus that this is a good depth. And so you'll do that. You'll do some kind of an aggregation. And the aggregation doesn't have to be a real sort of add all my neighbors together. It could be something more like a nonlinear diffusion process. But eventually you select a winning depth at each pixel. So this is a reasonably simple description of what a lot of stereo algorithms do. And it's actually a particularly efficient one This is what you would find in the real-time software implementations because it involves shifting pixels, computing their squares or sometimes even absolute differences, running some kind of a convolution operator, which can be very efficient to do the aggregation, and then picking a depth. Okay, now the alternative to this kind of a let's try all the depths, let's accumulate evidence, and then make a decision is more let's formulate one global cost function and minimize that. In a sense, the aggregation step is doing a kind of a cost function, but it just says for one pixel, look no more than a certain window away, and then make the best decision. Whereas these things are more like, okay, we know what the individual matching costs are. Now let's find a solution where the matching costs are good at each pixel, but each pixel tends to be close to its neighbor in depth. We do allow pixels to have breaks in the depth. We penalize that, but only by a certain amount. But ultimately, let's see if we can come up with things which look like, well, most pixels are in sort of contiguous depth regions. So this is a very classic approach. The first formulations go back to the early 80s, and people were using simulated annealing in the mid to late 80s. That was a popular technique now. The most recent work in this area is being done by Raman Zabi at Cornell, also Davi Geiger, a couple of other teams, which are using combinatorial optimization techniques, graph cut techniques, to minimize these problems. It turns out that you can use max flow, min cut kind of algorithms to come up with quite good approximating solutions to the problem. And those seem to be the most promising solutions. I was working with Daniel Sharstein a few years ago on a different algorithm, which is kind of it's not Monte Carlo in the sense of simulated annealing, but it is a probabilistic algorithm. It updates probabilities. It's actually closer to the loopy belief propagation that I think some people were talking about here a few months ago. And the advantage of this is because you don't have a fixed window. You're just sort of saying, well, I'd like to be like one of my neighbors, or as many of my neighbors as I can. You end up with much crisper boundaries than you do if you just have these window-based techniques. Okay. Now, in general, with all of these techniques, these plane sweep stereo algorithms, you still have the problem that if a certain part of the scene is only seen from one camera or from a subset of the cameras, you have this step where you're saying, okay, everybody vote on this location in space, and then let's see what's happening. And some people shouldn't be voting because they're actually on a foreground object. And so what we'd like to do is to get rid of that problem. And also, I haven't yet told you how we're going to treat these partially transparent border pixels. So let's see how we can modify the basic plane sweep algorithm. Instead of thinking of this as just a plane sweeping back through space, why don't we think of it as a collection of planes which are made like acetates. You're allowed to paint on the thing. This is the way cell animation is done. And furthermore, the paint you use can be a watercolor, so it can be partially translucent. If we do that, then we can probably describe a scene like this tree in front of a house as a cutout for the tree in the front and the house in the back, and its appearance will be different in each of the images. Okay? So this is a kind of stack of acetates model. This is what Polina Golland and I ended up implementing. And the algorithm is the basic plane sweep algorithm, but it's somewhat modified. Instead of, after doing the initial enumeration aggregation, instead of saying, okay, every pixel, what's your best depth? You just say, well, okay, which pixels are pretty sure they know what their depth is? In other words, if you have a low matching cost and everything else looks good, then you say, yes, I think I'm over here, and typically that means the regions which are fully visible can sort of commit to what they look like. And once those regions have committed to what they look like, they can be removed from the original images. You say, okay, I have accounted for these pixels in each of the images. Therefore, now try to compute the other pixels. And when you do that, then it turns out that the background pixels here are no longer contaminated by foreground tree pixels, and so you get better estimates. So you can sort of progressively remove things and get a description which is sort of like painting the volume with elements. And this is quite similar to what Steve Seitz developed about the same time. He calls it a space carving approach, and they would go front to back and remove things. We have a slightly different twist, which is more like removing the ones that match well and then going later. And I think Chris Bueller has been working on something like that in the last week or so. So this is the Voxel Coloring algorithm that Steve Seitz originally developed. He's been generalizing it with Kyros Koudelakos. They've been getting very nice results on data sets where they can see all the way around the object, and then they use dozens of images. He gets some nice three-dimensional models of dinosaurs and roses and things like that. So it's currently quite a popular technique. Now, what I've told you is how to sort of go get the pixels that are good, erase them, get the other pixels. So that deals with the partially occluded problems. I haven't really told you how yet to get fractional opacity. So the solution we came up with is, assuming that initial stage gives you reasonable results, but it's kind of gotten confused near the edges where things were of mixed colors, why not turn this into a continuous optimization problem where you start with the initial set of pixels and then you just do a gradient descent on the whole space of possible volumetric pixels. So all pixels that can have an arbitrary color in alpha will now do gradient descent, and we'll try to basically tweak the values so that each of the input images is reproduced as well as possible, while also maintaining a kind of smoothness on the color. So you penalize sharp variations in colors, or especially in terms of alpha opacity. And furthermore, it'd be better to have the scene described as a collection of mostly opaque surfaces rather than partially transparent washes. And this is actually a real problem, because without this final constraint, if, for example, I saw a wall which had on the background a checkerboard of light and dark blue squares, I can equally well describe that as a wall with a checkerboard of light and blue squares, or I can describe it as a wall with white and black squares with a transparent blue acetate in front of it. So there's an incredible number of possible descriptions, and so if you don't have the right priors, you won't come up with a description that you like. So here's the input images. This is that tree sequence I showed you before, and this is just the first 3 images. And now I'm going to show you the layers back to front that it's recovered. So what you're going to see here is kind of a confounding of different things. The pixels that are dark are the pixels that live in that layer. So as I go forward, you're going to see the parts of the tree that are in the foreground sort of come into focus. So here is the very frontmost part of this tree here. And then as I go back again, you see the next part of the tree. It's sort of like peeling away the layers. And I've also encoded in this image the actual color values. So you'll see on the front layer, this is sort of lighter here and darker there because I'm peeling away color values. And the only way you can tell which parts are invisible is I'm going to tell you that white is invisible. So when you see things that are extremely light, you have to sort of interpret. It's just generally hard to sort of interpret these images with invisibility unless you have a backing color that is quite different. So probably for this example, I should have used a different backing color so you could see what was going on. So again, back to front, this is what it looks like. And what I'm going to do to test the algorithm is I'm now going to take one of the original input images and put a mid-ground blue square somewhere inside this, so somewhere behind the tree but in front of the background. And this is kind of one way of telling by eye whether the algorithm's doing well. Because anywhere it makes a mistake, you will see a little bit of sort of gray cruft that shouldn't be there. So it sort of thought there was maybe something at this layer, but it wasn't very opaque. And it's there in front of this blue. And again, you can see that the edges aren't quite right. So, frankly speaking, the quality isn't as good as I'd like it to be. I think the problem formulation is good, that we eventually want a description of the world that has partial opacities. But the current algorithm, because of the large number of degrees of freedom and, the particular heuristics I use, doesn't work as well as I want it to. So, we had some partial results, but I think it's still an open problem. So, as I mentioned, the advantages of this technique is that we can take as many images as we want, and that in principle, we deal with occlusion and mixed pixels, but we probably have too many degrees of freedom. And also, because we're enumerating this thing with a set of acetates at different depths, we basically end up voxelizing the space. So if you sort of render each of these acetates into different images, you will sort of potentially see the sort of sliding of things in different layers. So there's no sort of concept of a particular pixel lying at a sub-pixel depth. The representation could probably be tweaked to do that, but we didn't get around to it. Okay. So this is the first of 3 algorithms I'm going to present. I think I'll have enough time to run through this, but just keep in mind that this was our first try. That was done with Polina back in 96 and presented in early 98. Then Simon Baker came in the summer of 97, and together with Anandan, we developed the following variant, which is still, let's keep that intuition about describing the world as a collection of painted acetates, but let's sort of generalize it and simplify it at the same time. So rather than having a large number of acetates that are stacked on top of each other, let's just put down the correct number. In other words, let's associate one with each layer in the scene. So it's not necessarily each object, but it's sort of foreground, midground, and background. Let's describe each of those as a layer. And then let's paint the colors back onto these things. But these layers can be oriented. So if one of our layers happens to be the ground plane in a room, great. We don't have to dice it up into lots and lots of little overlapping salami slices. We can just represent it with one plane. So the way this works is that in any particular input image, we can assign pixels to layers. And this is the result of doing a rough hand painting of which pixels go to which layers. You'll see the layers consist of 2 layers for the background, 2 for the midground, and 2 for the foreground here. Once we know, or we've guessed, which pixels belong to which layer, we can register all the pixels within a layer. And this is where the older work I'd done on image mosaics comes into play, because, as I mentioned before, the relative motion between pixels that lie in different layers are these homographies, or these perspective projections. So we can run a mosaicing registration algorithm to figure out what the registration is, and from the results of that registration, we can compute the plane equations. In fact, given enough of these things, we can actually even compute where the cameras are. So potentially, although this isn't the way I prefer to run it in practice, potentially you could do this as get some initial matching of different regions of the image, and simultaneously back out where those regions are in space, their location, and where the cameras are. It's all doable in principle. So we could do that, and then we could say, okay, now that we have these planes, we've basically glued pieces together, we can then reproject them against the original images, and again, in principle, figure out which pixels do belong there and which ones don't. Although if you look at that carefully, it becomes very subtle, because if a pixel isn't originally in there, then it's very hard for the algorithm to say, oh, I think we should put one there. All it can kind of do is to carve away things. And this is something that we didn't actually finish to our satisfaction. But as a representational framework, we're quite pleased with this. We think it's, for many scenes, it's not a particularly good representation for something like this can, if you've seen it from all different directions. But the way this room appears to me, if I'm just sort of moving back and forth here, I can say that, there's one plane describing this foreground thing, and then there's a bunch of cardboard cutouts in the scene, and then there's a background thing. So for a lot of scenes that we get, this is a very reasonable description. And so then we have the final collection of three-dimensional objects, or sort of cutouts. And what we've done is, to make this thing more realistic, we actually added, in addition to having just the cutouts, we can compute a out-of-plane depth. And so we can actually get that sort of sub-pixel precision we want. So think of these things as not being as flat cutouts, but as embossed cutouts, the kind of thing you get on the plastic relief maps that you can buy sometimes. And the advantage of doing it this way, we get a better fidelity, so we can describe scenes with more fidelity. But also from the computational point of view, the stereo algorithm has an easier task than the general one, because it doesn't have to figure out occlusions. If the layers have somehow figured out which pixels occlude which ones, then the stereo matching algorithm is just this simpler problem of, okay, figure out for each pixel what the depth is, but don't worry about pixels occluding each other, because within the layer, the assumption is that they won't. So, we can, the sort of mathematical foundation for this is what Anandan and his colleagues developed as plane plus parallax. The actual stereo matching algorithm has been called by Paul Debevec as a model-based stereo, because you have a rough idea of the plane with respect to which you're doing it. And it gives us generally better accuracy. From the rendering point of view, we have this slightly tricky technical problem that if you have a image with a Z-map, a depth image, and then you want to view it from a different view, in principle it involves some kind of a forward mapping, like a splatting. But with Michael Cohen, we developed some approximation algorithms that work quite well for rendering these things. So this is sort of the second major new thing algorithm we tried and I wanted to present. So the advantages are that it does do a nice accounting for what's occluded. You can see things that are behind and in front. You can, in principle, at least represent pixels that are transparent. And Ron Drower is working on that issue this summer. He's trying to actually get the algorithm to compute what the correct transparent pixel values are along the edges. And also, as a side effect, once you assign pixels to a particular layer, even if you don't know what their exact depth is, you can just sort of default it to lying right on the plane. So it has a nice kind of byproduct that fills in regions where there might not be too much texture. But it's still not a finished story. For one thing, we don't have currently yet a good initialization for the system. In other words, we don't have an automatic technique that figures out the number of layers and which pixels go where. Phil Torr, when he was here, worked a fairly nice framework for doing that. We've gotten some initial results, but they're not yet comparable to what we're getting by hand. So that's another open problem. Okay, let me present the latest thing I've been doing on stereo, and then we'll move on to not stereo, but just more general 3D modeling. And this is the idea that, well, perhaps trying to go to a layered representation directly is too difficult, because that requires sort of saying which pixels go where. What if we could just, go back to the initial problem, which is computing a depth map, and ignoring occlusions, at least, the depth map problem isn't that difficult, because you basically just enumerate all the depths and then pick the ones that match everything the best. But now, instead of doing this just for one image, so this picture here, which might seem a little bizarre, is a cross-section through a sequence of images. So what's happening is we're looking at the flower garden sequence, where there's a tree moving in front and some bushes, some flowers in the back. And there's a tree here moving from right to left this way. And so what's going on is that think of all the images as you move the camera being stacked into a volume and taking a cross-section. You can see that the tree, as it moves, occludes certain things. So if I just compute a depth map, let's say for one of these images, I won't be able to predict what this image looks like, because it would have occluded some of the pixels. And yet, if I computed a bunch of depth maps, or let's say I want to resynthesize this viewpoint here, if I just took a view from here and computed the depth map, as soon as I move over here, there are disoccluded regions. But if I took it from two different points of view, there's some hope that I'll have seen enough of the background so any intermediate view can be done. So this is arguing that let's try to compute multiple depth maps simultaneously, and thereby have a representation that has the power to at least reconstruct all of the input images. And furthermore, our claim is that we can actually figure out which pixels are partially visible using this representation. So I'll show you. The potential advantages are that we don't have to discretize space. We're back to sort of the simplest depth map computing problem that I gave you, except you're doing multiple ones of those. We can, as I'll show you, figure out where the occlusions are. And furthermore, if there is any variation in appearance, so let's say if, as I move around the room, the shading is a little bit different, things are specular and the specularities come and go, for a range of nearby viewpoints, hopefully those will be similar, I can do sort of a local stereo match. And by having multiple images and multiple depth maps, I can resynthesize things in a variety of places. So it's sort of, the argument is that you don't just have to have one 3D model with one texture map to recreate the world. You can have multiple views with the depth maps serving as sort of hints as to how to map between views. It's also a nice way, it's related to what people do in MPEG, but MPEG is remarkably simple-minded compared to this. You typically compute motion vectors by just taking pairs of images, and you interpolate a couple of frames, and then you take the next pair and interpolate. And this sort of says, well, what about if we sort of did this all along and somehow made sure that all of these motion vectors were consistent? That's kind of the direction in which I'm pushing. So mathematically, what we're doing is we're trying to solve a global optimization problem which sums over all the keyframes S, a measure which involves the neighbors of S. These are temporal neighbors. So think of a large sequence of images. Think of, let's say, taking a moving window of 5 images. So every keyframe has plus or minus 2 neighbors. And there's a little weighting term here if you want to weight your nearby neighbors more. But basically, we're trying to match corresponding pixels. So pixels that go together from one image to another, we want to make sure that their intensities are the same. And instead of squaring the values, we put a little robust penalty function, which means that beyond a certain point, if the 2 pixels don't match, you don't care how much they mismatch by. The general framework was developed both for motion, where you assume that things are moving relatively smoothly over time, this kind of motion, and rigid scenes, where you assume that once you know where the cameras are, everything is explained as the mapping of points and depth into cameras. And we use these robust penalties I don't want to really go over. So I gave you a formula there just to give you an intuition about the elements. But the actual formula has 3 terms. The first term is what I already showed you here with the robust penalty function, but we can generalize it to include a visibility term. If we have things like bias and gain between images, we can throw that in as well. The important thing is that we have this visibility term, which says when we're going to match 2 pixels, don't penalize pixels which aren't possibly visible. So if we're going to match, let's say, something to the left of this house here, like the peak of that roof, which is occluded in this image, we won't pay a penalty. And I'll tell you in just a second how we compute that visibility. Furthermore, because we were computing multiple depth maps, what we really want is these depth maps to be consistent. But there's no easy way in an optimization framework to match up things and put them in as hard constraints. I mean, you can, but the fact of the matter is that the depth at a particular pixel in one image will not always map to an exact location in another image. So it just gets complicated. So instead, we have this kind of a soft kind of constraint, which says, well, we'd like to make sure that depths at corresponding locations or vectors, flow vectors at corresponding locations, are somewhat similar to each other, but we put it in as a soft penalty. And then we also want to make sure that things just aren't salt and pepper and noise all over the place. So we put in a fairly standard smoothness constraint. And one thing that's somewhat novel in our work, although I think Raman Zabi was telling me they do the same thing in their matcher, is you can actually make the shape of this function of whether you want two depths to be similar a function of whether their colors are similar. So in other words, where you have intensity discontinuities, color changes in the image, you can say, I care less about the depth being constant here. And what that means is that if you have two regions of different colors where their colors are their depths are indeterminate, it will tend to locate the depth discontinuity where the intensity discontinuity is. And that gives you crisper discontinuities. So let's talk about sort of what is probably the key insight in this paper, which is we can compute visibilities if we're given more than one depth map. And the way it works is this. Let's say we're talking about that problematic pixel that lies just to the left of the tree here. Well, I can tell by eye that that pixel is not visible. The tree moved in front. Okay, but I can only tell that because I know, there's a tree and stuff. Can I do that based on the depth maps? Well, if the depth map somehow managed to figure out correctly that this pixel was at this background depth, it will say, okay, that pixel lies here in the other image. And it does. It really does lie there. It's just that it's occluded by the tree. So if the depth map algorithm has correctly computed the value for this tree, then it'll say, oh, okay, well, there's a tree in front of you, so you can't possibly be visible, and therefore the normal matching penalty between these two pixels, which would say, oh, this isn't a good depth because, you don't match in color, will be disabled. And therefore the algorithm, in principle, can come up, if it could find the minimum of this cost function, would drop into that energy minimum. So that's how we do visibilities. When you have depths which are ordered in depth, in other words, I can say, let's say, small values of, typically these Ds are inversely proportional to Z for reasons I don't want to really get into today. But in any case, you can tell by comparing depth values what the foreground is and what the background is. So that's nice. For general motion, if you have two things moving in front of each other, it's hard to say if the faster thing is the occluder or the slower thing, right? In this case, the faster thing is in the background. In this case, it's in the foreground, right? So for general motion, you can't tell what the occluders are. So we come up with this weaker thing which says that, well, if you can't agree what your motions are, then probably both of you will just disable the visibility of both of you. So, okay. So the algorithm works in two phases. First of all, we compute a depth map for each frame, and then after we have initial depth maps, we can recompute visibilities and try to optimize the whole thing. So I don't think I really want to go into this. This is an implementation detail about how we use a combination of course-defined searching. Those of you who've been using this algorithm this summer know that it contains this course-defined thing together with some sort of a local search. And I'm going to skip over that. So these are just some sample results. If we do the initial depth mapping, and then we say, what does the image look like if we try to resynthesize this image here by mapping pixels from the first image, then you'll get this kind of contamination. And I think at this point I'll just show a quick demo because that shows it off better. What we have here is a collection of 5 input images, and we've taken the middle image and I think its left neighbor and run some stereo matching algorithms on it. Okay, so this is what the input looks like. You can see that for example, the lamp is moving in front of the background. Okay, now if I go to the middle image and I say look at the depth map, this is what the depth map looks like. Is it showing up on the projector? It's I think I can darken it a little bit there. So it has the foreground lamp and quite well, and the background well. So you may ask, why is the quality of this thing so good? Well, this is the ground truth that was labeled by graduate students in Japan. This is, as far as we know, the only stereo data set which has ground truth data associated with it. So we've been using it a lot to debug our algorithms. But the interesting thing is they went through and they said, okay, these pixel values here have a depth of 14, which means that between those two images where we did the matching, the pixel moved over for 14 pixels horizontally. And this one here has a depth of 6. Okay, so we have this depth image. Now what we can do is, if we know where the depths are, we can take any other image in the sequence and say what it would look like from the with respect to the middle image. So we call this stabilization. I think Anandan showed a bit of that for motion. So if I say view the warped images, this is what the stabilized sequence looked like. Okay? There's the stabilized sequence, and notice that indeed, compared to the original image where the foreground head was moving, from side to side, it's pretty well stabilized. But I don't know if you can tell this, but for example, is the camera in the background there well stabilized or not? It's much better than the original sequence, but it's not that well stabilized, even though we had a graduate student, somebody had a graduate student label this with ground truth. And the reason why it's not stabilized is that they only labeled it to the nearest pixel. And pixel accurate correspondence just doesn't cut it. I mean, it might cut it for something like recognizing an obstacle, but for doing things like generating new views, it just doesn't work. Things swim, nothing moves. And if we were to actually take the scene and reconstruct it and move it away, you'd eventually see this scene being sort of a stack of acetates. So I took this data set and I ran a stereo algorithm, just a pretty brain-dead stereo algorithm on it, which said, take the initial value and don't move away by more than 1 pixel, because we believe that modulo rounding error, the graduate student got this right. And then if I show you the stabilized sequence for this, other than the back, top, and outside edges where they didn't label it, it's much, much better, right? Everything is basically stabilized. So this is what you want the algorithm to do. Now, the other reason I ran this was I wanted to point out that what's happening in the background there. What's happening is that for this leftmost image where there's, or let's say the last image here, where there's like a double image, what's going on is that in the original image that we're sampling from, we're trying to say what would the middle image look like if we used the left image as the source. That part of the background wasn't visible. It was occluded by the head, so it's pulling those pixels from the background. And that's where here in my talk I was going to move next to say, if the algorithm is working correctly, it can actually flag these pixels and say, oh, these pixels, by the way, are occluded. So it says, in the reference frame of image 4, if you pull pixels from 1, these pixels to the right of the tree aren't visible because the tree just clobbered them. So this is kind of the intuition about visibility. We want the algorithm to be able to reason about what is occluded and what isn't. I'll just show you one more thing here, which is what the algorithm does running just some stereo algorithm. This isn't even Raman Zavi's best stereo algorithm. If we look at the flow map, it's sort of like this. So it's somewhat noisy and a little bit blurry. But if we say to look at the warped images and then play them back, just swapping in, it actually does quite well at, in the foreground here, at the camera there. So it's doing reasonably well. It has the same kind of hallucination problems to the sides. And then it has sort of more of a pixelated thing. So I guess the message here is that if you're trying to reproduce new views, you don't have to get every last pixel right, especially like in uniform intensity regions. But eventually we would like it so that the resynthesized images are of high quality. So, okay, there's experiments. The advantage of this technique is you don't have to actually figure out how many layers they are, and it has fewer degrees of freedom than a full volumetric. But it actually doesn't do mixed pixels. So we see it more of a technique to either be used inside an image-based rendering loop or maybe as a preliminary stereo matcher to then do a layered description. Okay, let me quickly wrap up just to sort of show you a little bit more breadth in terms of the way you can slice this problem. Reconstruction isn't all about going from images to depth maps. You can also do things like volumetric models, like this kind of thing, where you take a scene. This is really the simplest thing to implement. You just threshold out what is the background. If you photograph this turntable when it's empty, you can say, oh, okay, only these things are in the foreground. And the algorithm will make slight errors where, let's say, something is moving, like the rim of this thing. But by and large, it's not that hard to figure out where the foreground is. And then by taking these images from multiple points of view, you can basically intersect them in space and carve out a region within which the object is known to lie. And this carving will be conservative. For example, the inside of the cup is really empty, so this should have a dent. But for many of the silhouettes, you can't tell. You would actually have to match pixels inside it. So it sort of gives you a conservative bounding volume. And it's very, very easy to implement. It's the kind of thing that you could throw at students in an undergraduate class, and they shouldn't have any problems. Another way of doing this, again, just to show you that matching isn't all about putting pixels into correspondence, is you could take a collection of images and extract edges, and then you could match edges. And some people say, well, edges are better than pixels because if you have a lot of variation, let's say you have automatic gain control on your camera, the edges will stay put, but the pixels will change in appearance. And to some extent, that's true. But eventually, when you get very high texture, the edges start becoming very jumbled, and it becomes sort of questionable whether you can match on them. But if you have enough images, those sorts of accidental correspondences start to go away. And you can actually match things and get, this isn't a particularly good illustration, but you can actually get a reasonable set of profiles and contours. And in particular, this technique is particularly good at getting the outside edge of an object because it doesn't insist that all of the edges land at the same place in 3D. It can actually detect the fact that the edges are on a round self-occluding contour, and it'll actually compute the correct place where those edges came from. So it has advantages in that sense. So that's another way of approaching it. And I don't have much to say on this topic. I want to throw the slide in because this is sort of the second half of the problem is even once you have the shape, you still have to figure out what the objects or the world looks like. So there's this problem of even if I can back out the shape, what is the appearance of the object? And in particular, if the scene is like illuminated with some lights, what you'd really like for graphics applications is to know the true colors of the object, not the color with the shading on it. Because if the shading is with the object and then you rotate it by 90 degrees and put it back in the scene, it'll have the wrong shading. So people are working on this problem. I don't think the results so far are that widely applicable. They're nice results, but they work in certain special cases. Like, for example, the and Malik work depended on taking scenes of architecture at multiple times of day. So as the sun was moving by, they could eventually factor out the sun illumination and the sky illumination from the natural color of the object. But it's an active research area. I think Zhenyu Zhang is very interested in this. So I showed this at the beginning just to sort of show you a complete end-to-end system. We can combine the output of this kind of octree thing with 3D curves for better accuracy around the edges. Then we triangulate the model, and we paint color back onto it. So I think this is, I'm wrapping up. So let me just sort of present to you a variety of ways of skinning this problem, right? So probably the simplest way to take multiple images and get some shape information is to compute a depth map. And we know that this can be done at just about frame rates on PCs today. You can buy systems for point gray which feed 3 cameras into a digitizer board and then run a correlation algorithm. If you want to be more sophisticated, in particular if the scene is being viewed from many different views, so lots of things are occluding each other or there's a true three-dimensionality, then you want to have something that's more volumetric. The volumetric description is a much more natural one when you're looking at things from different points of view. And I would argue that treating opacity as part of the problem gives you a more powerful representation. That's what you want to do. For scenes where things are nicely separated into different occluding layers, then this layered representation is very powerful. We can get some very nice three-dimensional impressions. We can resynthesize the original image. We can interpolate frames. So that's a very good representation. But we're still struggling with some of the basic issues like how to initialize it and how to refine it. Multiple depth maps are another way of going around the problem. They address some of the problems of partial visibility that you get if you only have a single depth map. But on the other hand, they aren't a single consistent representation in that the depth maps can in principle disagree, although the algorithm tends to encourage them to be consistent. And then we have other things like you can match curves and put those in. Or something I didn't even mention, but you can also think of the problem as kind of an elastic kind of a rubber mesh or a shrinking balloon or something that fits the data directly. So you can think of floating a mesh in space and then projecting images against it and then having the triangles on the mesh deform in a way that the projections are as consistent as possible. And Faugeras and a colleague have done this as a sort of a voxel carving approach where they start with a large sort of sphere and shrink it in on the object until it stops at the places where things match well. And they happen to actually use an implicit function formulation. So rather than having a mesh where you have triangles controlling the mesh, you have a grid, and the values, the sign values on the grid, their zero set defines where the surface is. And since we're talking about representations, I should just point out that while in general we tend to think of the representation as some, static quantity that we're trying to estimate, underlying this whole thing is an estimation problem. And in some cases, it might be advantageous to think of distributions. For example, in people tracking these days, it's very popular to use these condensation or density estimation techniques that keep multiple hypotheses around. And when you're unsure about where the tracked object went, you can sort of split off hypotheses and then later relatch. So there might be possibilities to include sort of more probabilistic formulations in here. And then to summarize the algorithms, again, just sort of give you a range of the kinds of things that can work. You can do correlation. You can do other kinds of aggregation. Using a pyramid is very often a very powerful and useful thing to do. You can do some kind of a gradient descent or with noise that becomes simulated annealing. Mean field is another approximation where you actually model the distributions across all the pixels. You can choose to compute explicit visibilities, and in some of the formulations, there's actually kind of a segmentation or grouping problem lurking underneath. So you may have those kinds of algorithms involved. And I think that's where I'll stop.